Hey, how's it going? So today I'll quickly talk about the solution to Pramp's k-masked array sort. So given an array of integers where each element is at most k places away from its sorted position, code an efficient function sort k-masked array that sort array. For instance, for input of size 10 and k is 2, the element belongs to indexes, and the sorted array will be located at index 4, 5, 6, 7, and 8. Analyze the time and space. So basically what this means is that, let me write my index here. Yes, so basically these are the index of the elements. And k sorted k array means that k equal to 2 means that at index 0, the correct uh, the correct position of this number is like almost 2 numbers away. So basically, at index 0's position, the result is gonna be a number within this range, and at index 1, it will be within this range because k is equal to 2 and this number is like 2 places away. And at index 2, the correct answer will be within this range because this left bound and right bound are 2 places away from this position. So basically, our output should be the sorted array. So if you can, the brute force will be just return sorted array, but this will be n log n. So can we find something that is better than n log n? So we can find it in actually n log k. So how do we find it by n log k? Because we know that at each position, our it is within a range, so we can keep a size k heap, right? So we can use a heap. And what would be the would be the elements, the numbers in the heap? So first of all, like by keeping a size of k something, then we can do n log k, right? So that's obvious. So how does that exactly work? And what would be the number of the elements in our heap, right? So we will actually initialize the heap, let's call it Q, to 3 numbers. The heap will be the first, the k plus 1 numbers. So our heap will be initialized like this. And we have a read and write pointers. So basically, we can achieve n log k time complexity and O1 space because we can use a read pointer and write pointer. So basically, this write pointer will write the index, so we don't need to create an additional result. We don't need to create a additional like list as our result output. So it can save our OM memory to O1. So how does that exactly work? So first of all, I initialize my heap as the first k plus 1 elements. Then I have a read pointer. This read pointer will go from k plus 1 all the way till the end. And what it's do is that at each place, I pop the smallest number from my heap and write it to my right pointer. After that, I append the read pointer's number. So you can see if my read pointer start at k plus 1, so let's say our result array will be what? Will be, at this point, we pop the smallest number from our heap, that's 1, right? And we append our read pointer's number, that is 2, right? And we increment our read and write pointer. At this point, I pop the smallest number from my heap. So that's 2. I pop that and also append my read pointer's number, which is 3. At this point, I again pop the smallest number from my heap appended to my result array, and then append my read pointer's number to my heap. And at this step, again, I pop the smallest element from my heap and append it to my result list, and append my read pointer's number to the heap. Here again, append my heap pointer, my read pointer's number to the heap. Here again, my read pointer's number is 10. Here, I pop the smallest, append it to here, and I append the number. Okay, right now my read pointer is at the end of the heap, and you can see that my result is here. But we have to loop through the last, we have to pop the smallest element from our heap and append it to our result. So the smallest right now is 8. So we append 8, and the smallest is 9. We append 9, and the smallest is 10, and we append 10. Yeah, this is how basically the algorithm works. You can compare the result to our expected output, and you can see that's the same. So basically, we keep a heap of size m plus k, k plus 1, and we append the first k plus 1 elements to our heap. So that's our initial heap. And then we take advantage of the heap, the write and read pointers. And our read pointers will be from k plus 1 and all the way till the end. So at each step, as we see before, our write pointer, this is our write pointer. It is read minus k minus 1. Write pointer will be the smallest from the heap. So we pop one element from the heap, and we append, push the read pointer's elements to the heap. So at each step, our Q is always k plus 1. And then when our read pointer reaches to the end of the array, all we need to do is to pop our current heap. It should still contain k plus 1 elements, so we loop for I in range k plus 1. So this is like calculating the right point, our previous pointer. So basically we have to calculate the pointer for 7, 8, and 9. And once you figure, you can just try how to find it, and you just pop the smallest element from the queue. And in the end, because your array is written as you execute your algorithm. So at the end, you just need to return array. So the time complexity will be O log k, and the space will be O1 because you are not creating any additional. I guess the space complexity is probably okay, maybe because you have this Q elements. So yeah, it should be okay. And the time complexity is n log k because you loop through each element, and each time you just need to know the smallest elements. So that's gonna be n log k time and OK space complexity. So this is actually a little bit tricky to know how to initialize the like the queue in size k+1, and also like use the read and write pointers. So it's a little bit tricky. Okay, thank you.